We're going to take a look at sections 3 and 310 together, and those topics together would be functions and relations. Our objective is going to be to diagram relations and determine when relations are also functions by defining a function, and then find values of functions and graph functions. First, a relation. A relation is a mapping or a pairing of input with output values. For example, you put a certain value into some sort of a system. You put the value 4 in, it goes in and some operation is performed, and then what comes out, let's say, is the number 8. So this operation that's involved here could be +4, it could be ×2, it could be something else. But this would be like your input right here, and this would be like your output right here. So a relation is just a pairing or a mapping, again, of inputs and outputs. Now, traditionally speaking, we consider these to be x and y, and we're used to that, where we have some sort of xy table, and we have x and y here, so like 2, 7, 3, 5, 4, 9. So those quantities there that you're seeing, the inputs are the x values, because you're plugging x into the actual relation. Then what's coming out is going to be the value for y. So the inputs are 2, 3, and 4, and the outputs are 7, 5, and 9. Now, before we can go any further, we need to define some terms. First, independent variable. The independent variable is traditionally known as x, but this is the variable of choice. Okay, it's assigned a value of choice. So you plug in a value for the independent variable. Now, what you get out is actually the dependent variable. So what we're going to see is that this is like a cause and effect. You plug in a value here, and what comes out is whatever this is. So you plug this into your relation, and you get a value out for the y value. So we're going to say that the independent variable, this value here, is the cause of it. Now, if we think about a graph, and we were to graph these points here, let's graph the point, the first one, 2, 7. So I go over 2, and I go up 7. I'll make that 5. Okay, so I go up to 7. 7 would be up here. So there's my coordinate, 2, 7. Well, what did I do? We plugged in the value of 2 for x, and what resulted in was 7 here. So another thing, instead of calling the independent variable the cause, and this is being the dependent variable is the effect, we could say that the independent variable is the width of the curve. Okay, the width of the curve. So let's imagine that we had a graph that looked like this. Okay, and that's what the graph looks like right there. Well, the width of the curve at this location is right here. Okay, so we take this value and we drop it down here, and that's the width of the curve. Okay, how far it goes over, the width. It's the independent variable. We consider independent variable to be the domain of the function, and the dependent variable to be the range. So let's take a look at the range now. For the range, we'd have to take this value and trace it over here and see what we intersect with, and this is our 7 right here. And this would be considered to be the height of the function. That's how high up it goes. It goes up to 7. So we'd say that that is the height of the curve there. Now, the dependent variable is drawn along the vertical axis, and the independent variable is drawn along the horizontal axis. So please remember that x and y are the common terms we use, but they're not the only ones that can be used. For example, a common graph that you're going to see, especially in physics and calculus, is distance and time, or displacement and time. And in this case, let's say our graph looked like the following. Okay, the distance is along the y-axis, so this is your dependent variable. D stands for distance, though they're not dependent, and this is your independent variable. And think about this for a second and make sense of what's going on. If you're running along a track and you want to find out how far you've gone, if you run for a longer time period, you will go further. So traditionally, we say that there's like some sort of, direct relationship between the time you run and the distance you've traveled. So this distance depends on what time you're actually looking at. So if we were looking at a person just running on a certain path, then the function would look like the following, really. Maybe a linear function increasing. Because as time goes on, they run a further distance, so it keeps increasing. So you spend more time running, you go further. You spend even more time running, you go even further. So this is what you're plugging in. This is, in a sense, the independent variable that you're using, and this is what you get as a result. So this is your cause, and this is the effect. Now, relations can be represented in 4 different ways. So again, remember, relation is just a mapping. So we can look at ordered pairs. So these ordered pairs here that are given can also be written as a table. And take a look. These are the ordered pairs. The same values are in the table. But you could also graph these four. Negative 2, 2 is here, negative 2 is here, 0, 1 is here, and 3, 1 is right here. So we could graph these. So those are the first three ways. The fourth way is a mapping diagram, which may be new to some people. We'll notice, though, that negative 2, its output is 2, or it's negative 2. So this has two different possible outputs from one input right there. The input of 0 and 3 happen to both go to 1, so those both go to the same output. Okay, so again, 0 goes to 1, 3 goes to 1, that's why they're both going there, but the negative 2's go to different values, so that's going to split apart. Keep that in mind for the next thing we do here. Now, a function is simply a relation for which each input has only one output. Only one output. So let's take a look at a data table. Just pick random numbers here to see. So let's say we have 1, 4, 1, 7, 2, 5, and 3, 8. Well, if I look at this one, I'm going to see here that the input of 1 has two different outputs. The input of 1 can go to 4 or it can go to 7. So a mapping diagram here for this one, with our domain and range, a mapping diagram would look like the following. But the 1 happens to split to both of these, whereas the 2 goes to 5 and the 3 goes to 8. So the problem is that, remember, a function is defined as each input has only one output. But clearly this input has two different outputs. This input here has two different outputs. So this would not be a function. Okay, this is not a function, this example right here. An example that would be a function would be like, maybe we just change this to negative 1 suddenly. And now this doesn't have the same thing coming from each one, so it would change our mapping diagram. So our mapping diagram would now have a negative 1 in there as well, and that negative 1 will be going to 7. Okay, so we can get rid of this portion right here. Make believe that's not there. And now we'd have 4 different inputs with 4 different outputs. If we graphed these 4 here, and we take a look, let's go back to the original way we had it with a positive 1. Okay, so let's go back to making that a positive 1. So we have the first coordinate graph would be 1, 4. Okay, so I'll go over 1, up 4. Here I'll make 4. And I'll make this 8. So here's 1, 4. Here's 1, 7. Here's 2, 5. And here's 3, 8. What you'll notice is that the part of this domain and range that causes this to not be a function is this repeated 1 here. Remember that repeated 1. This input has two different outputs. And notice, this coordinate 1, 4 is right here. This coordinate 1, 7 is right here. So what we'll see is that these actually lie on the same vertical line. There's a vertical line here that they both lie on. So whenever we have 2 points that lie on the same vertical line in a relation, that proves that it's not a function. So what we're going to see is that if we could ever draw a vertical line that goes through 2 points, it is not a function. And we're going to call this the vertical line test. So let's take a look at this example one. Graph the relation 1, 1, 2, 1, 2, 1/2, 3, 1/3, 4, 1/4. Notice right away before you start graphing this that it would make sense in this example only to go up to 1 along the y-axis. And maybe we can draw like a half is there, there's 3/4, there's 1/4. And along the x-axis, we're just going to go to 4. So 1, 2, 3, 4. So if you're graphing in these examples, please take a look at your domain and range before you pick what your axes are going to look like. All right? Let's go ahead and graph these. 1, 1. Where's 1, 1 going to be? That's going to be up here. 2, 1 is here. 2, 1/2 is here. 3, 1/3 is going to be around here. And then 4, 1/4 is around there. So in this example, we're going to see that this input of 2 has two different outputs. So this is clearly not going to be a function in this case. And the way we can also check graphically is simply by trying to fit a vertical line on this graph. So let's take a look at what I'm saying here. If I bring up a vertical line. Okay, let's go ahead and take this vertical line and move it. Now, if I take this vertical line and just slide it back and forth, there's only one intersection, only one coordinate matches here. Only one coordinate here and one here. But here we're going to see that at 2, this vertical line goes through 2 coordinates. And this is called our vertical line test. You can literally take your pencil and just hover over the graph to see where it intersects. If it intersects in more than one spot, then it is not a function. It is not a function. So this would be a relation, but it's not a function. So we can generalize and we can say that not all relations are functions, but all functions would indeed be relations. So if you do have a function, it is a relation, but not all relations are functions. If we look at our vertical line test, this is what I was just referencing a moment ago, and I can show you again with the example with the vertical line. So if we had a vertical line, and we take this vertical line and move it, we'll see that no matter where we put this vertical line along this curve, there's only one intersection. There's only one intersection. So here's your intersection right there. If I continue to move it over, if I move it this way, well, still, again, one intersection right there. But the minute I take this line and move it over to this curve, we'll see that there's a lot of instances where there's two intersections. Again, intersection, intersection. No matter where I move this line on this one, it looks like there's going to be two intersections, except right here and over here. But if I can find just one point where there's more than one intersection along the vertical line, then it is not a function. Okay, so this one is not a function. Example 2 says, given the following with a domain, find the range of y, graph y, and is y a function? So let's go ahead and find the range. So we have to remember that our domain is the x values and the range of the y values. So this is what we have in this problem. And now all we need to do in this part is just plug these into the original equation. We're going to get 4 values for y. The first value is going to be 32, then 7, then 40, and then 82. So clearly here we're going to see that this has got to be a function already. Before we even graph it, we can tell because there's no repeated x values. So no inputs are going to be repeated. If we were to graph this one, I would graph this and make my y max 80 and make my y min 0. So let's put 80 up here, and we'll just go down to the bottom. Along the x-axis, let's go back to -5, and then we'll do 5 and 10 over here, so we have all the x coordinates. So again, please look at your actual range. This is the highest is around 80, and the lowest is around 0, so that's all we have to do for the y-axis. We can put increments. There's 40, there's 60, and there's 20, so that we know along the way. So let's graph these. The first one is going to be -3, 32. Well, here's -3 somewhere over here, right? We go back to -3, and then this is up to 20. We want to go up to 32, so it's like right around here. So let's go ahead and graph that point right there. Then next, we're going to go over to +2 and up to 7. Well, if this is 20, this is 10, so 7 is a little bit lower. So 7 is going to be just like right around there. So that's 2, 7. Then we're going to look at 5, 40, which happens to be right there, smack on the middle, on the crosshairs, or on the intersections of the grid lines. And then finally, 7 is out here, and 82 is up here. So we're looking at a point up there. All right, so 7, 82 is up here. If we go ahead and bring up a vertical line, we're going to see, and for this example, if we move this vertical line anywhere, there's only one intersection no matter where we go. So one intersection, one intersection, one intersection, one intersection. So this must be a function. This must be a function, again, because the vertical line test does pass for these 4 domain values and these 4 range values. Example 3, give the domain of each function. So what we want to do in this problem is think about the fact the domain represents the x coordinates. And sometimes our x coordinates are limited based on the actual function given. So for these ones here, example for the first one, we have to think to ourselves, what values of x would make that fraction undefined? Well, what makes a fraction undefined is when the denominator is equal to 0. So in this case, for the first one, we have to think about this and say, well, x squared plus 4 cannot be 0, right? It cannot be 0. So x squared cannot be -4 if I move that over. So what values would be the solution here for x that would make this -4? And those are the values that x cannot take on. But if you try any values, if you're squaring numbers, you always get a positive answer. So there's no solution to this equation. So there's no number for x that would make this denominator 0. Again, if you square any number, it's going to be positive. So this will always be positive. And then when you add another positive, you're never going to get 0 on the bottom. So this can take on any x value because, again, the denominator cannot be 0 in this problem because you're always going to square that x. So in this case, x can take on any value, so we can say that the domain is all real numbers. Okay, all real numbers. But the second example is a little different. Look at part B now. In part B, we take a look at that denominator. What would cause this denominator to be equal to 0? That's our question we have to ask. Well, the only things that would cause this to be 0 would be if x is 0, right? Because that would make that a 0. Or if x were negative 2. If x were negative 2, it would make this quantity 0. So if I plugged in 0 for x, this would become undefined because this is 0. If I plug in negative 2 for x, it would make this portion 0 right here, making the whole thing undefined also. So 0 and negative 2 are my domain restrictions. So we would say it's all real numbers except for 0 and negative 2. Again, part B domain is all real numbers except for 0 and negative 2. Part C, we have to look at the square root. And the square root can be a little confusing. But remember, for a square root, you cannot take a square root of a negative number or else it becomes imaginary. So what we need to do is take a look at the radicand, the number under the radical, the expression under the radical, 2 minus x. And we need to remember that this has to be positive. Now, it could also be 0. So we could say that this has to be greater than or equal to 0. Again, anything greater than 0 is positive. Anything equal to 0 is clearly 0. So let's move the x over by adding it. We don't have to switch the sign because we're not dividing by a negative. We're just moving the x over by adding it. And this tells me, if I read it from right to left, that x must be less than or equal to 2. Again, reading it this way. So I can rewrite this as the following. Okay, and that's my domain for this problem. X is less than or equal to 2. If I were to write that in the correct notation, it would look like the following. Okay? And let's take a look finally at part D. Part D is 2 over square root of 2x minus 8. Now, a moment ago, we said to ourselves, well, you know what? We can't have a negative under the radical, but we could have 0 or a positive. But in this problem, if we go ahead and do the same thing, if we say, okay, 2x minus 8 is greater than or equal to 0, just like we did in the last one, right? That's what we did in this previous one up here. We went ahead and set the radicand greater than or equal to 0. So it's tempting to set the radicand greater than or equal to 0 again. But remember that you can't have 0 in a denominator. So this can't be greater than or equal to 0. It can only be greater than 0. It can only be greater than 0. So we don't need this equal to sign right here. Okay, so let's move the 8 over. Again, it's only greater than, not greater than or equal to, because it can't be 0 because it's in the denominator this time. So x must be greater than 4. So our domain would be the set of numbers of x that are greater than 4. So in essence, what we're doing here is we're saying what values of x would mess up the function or cause the function to be imaginary or undefined. So we have to look for our denominators, and whenever the denominator equals 0, that's one of the problems, or under the radical. We can't have a negative under the radical, so we have to set our radicands greater than or equal to 0. So if you want a rule of thumb, let's go ahead and write it down. For denominators, okay, set that equal to 0 and solve. And that will tell you the possible values that x cannot be. For radicals, set it greater than or equal to 0 to make sure you know the numbers that can be in the answer. Okay, so this would tell you what is not in the domain. The result of that will tell you what's not in the domain. The result of this would tell you what is in the domain. And this is why it's a little confusing. And then the last part is if you have a radical in the denominator, set that greater than 0 only. And again, this will tell you what it is in the domain. So the first one tells you what's not in the domain or what x cannot be. But the second two types of problems tells you what is in the domain. All right, finally, our last part is taking a look at compositions. And compositions are pretty much evaluating a function within a function. So let's take a look at example A. Example A says find f of 2. Well, here's f of x up here. So just take this 2 and plug it in for x there. Well, that means that you have to plug it in there. So part A, f of 2 is simply 2 times the quantity 2 plus 1. So I've taken this x and I've replaced it with the 2 that's being asked for. So 2 times 2 is 4. 4 plus 1 is indeed 5. So part 1, f of 2 is equal to 5. Part B, g of negative 3 means plug negative 3 in for the g function. So we've got negative 3 squared minus 3. Again, I'm putting that in up here. I'm putting that in up here. So this ends up being 9 minus 3, which is 6. Part C asks for f of negative 2. So it's going to be 2 times negative 2 plus 1. 2 times negative 2 is negative 4, plus 1 is negative 3. Let's take a look at part D. Now, part D says to do g of f of negative 2. So let's write this down and talk about this one. Remember PEMDAS. PEMDAS says to start with your parentheses, but we happen to have parentheses on the inner part. So we can't do g of f of negative 2 until we know what this actually is. We need to know what that number is, but we actually did it in the last part, right? We figured out what f of negative 2 is. F of negative 2 was negative 3. So we can replace this green box here, f of negative 2, with whatever its equivalent expression is, which is negative 3. So replace this with negative 3, the whole thing. So this is really just g of negative 3. So again, I've taken this quantity and replaced it with negative 3, because that's what it's equal to based on the previous line. But we happen to know what g of negative 3 is, and that's from part B, so this answer happens to just be 6. Let's take a look at the last one, f of g of 5. First we have to do g of 5, and then we can plug that into f. So g of 5, we go back up to the beginning, we're going to plug in a 5 here, so it's going to be 5 squared minus 3. So g of 5, okay, is going to be 5 squared minus 3. That's what we're doing. So we're replacing this with 5 squared minus 3. Well, 5 squared minus 3 happens to be 22. So really we're doing f of 22. And if we plug in 22 into the f function was 2 times 22 plus 1. Again, plugging the 22 into the f function for x. And we're going to end up getting here 45 for our answer. So to summarize here, let's just remember the key important facts. First, if you have an evaluation of a function, simply plug it in for x to get the answer. But if you have a function within a function, you need to work on the inner part first. So evaluate f of negative 2. Get an answer for that. Let's say hypothetically your answer for a new problem turned out to be like 7. So if f of negative 2 is 7, what you're really doing is you're doing g of 7. So evaluate the inner part first, get your answer, take that answer and plug it into the outer part to then evaluate. So this is our example of composition of functions. Okay, if we had an example that said this, and the problem asks us to find f of g of x, well, there's no numbers involved anymore. So we'd have to take whatever g of x is and plug it into f of x. Well, this is g of x, so we have to take that and plug it into f of x right there, and for the x coordinate. So this would become 3 plus 2, this is the beginning part, but times that quantity. Now instead of x, we're plugging in g of x in there, so that's x plus 2. And this would end up resulting in 3 plus 2x plus 4, which would simply be 2x plus 7. So you could evaluate functions of each other as well, in addition to numbers or other variables. Your homework for this section is from 3/8 and from 310.